It's crazy how straightforward it's become to merge models and make mixtures of experts. Mixture of experts, MoE, combine transformer models for faster inference than single dense models. They consist of sparse layers, which replace the classical dense feed-forward network layers, and a router that channels tokens to the appropriate expert. Mixture of experts, MoE layers, are increasingly used in large transformer models to manage the high computational cost of learning and inference. These layers primarily select the feed-forward layers in each transformer block, which are a significant source of computing expense in larger models. Despite their benefits, MoEs can struggle with generalization during fine-tuning and require high memory for loading all parameters, despite only using some during inference. At this stage, it seems more feasible for most of us to either fine-tune MoE models on smaller datasets using methods like SFT-DPO or ORPO, or use Mergekit to combine models into mixture of experts. Model merging is a technique that combines two or more LLMs into a single model. It's a relatively new and experimental method to create new models for cheap. No GPU required. Model merging works surprisingly well and produced many state-of-the-art models on the open LLM leaderboard. Mergekit is a free GitHub project that aims to be able to create merges of pre-trained models that can be run entirely on CPU or accelerated with as little as 8 GB of VRAM. Many merging algorithms are supported. Unlike traditional MoEs that are trained from scratch, Mergekit facilitates the creation of MoEs by ensembling experts, offering an innovative approach to improving model performance and efficiency. The main difference between true MoEs and Franken MoEs is how they're trained. In the case of true MoEs, the experts and the router are trained jointly. In the case of Franken MoEs, we upcycle existing models and initialize the router afterward. In other words, we copy the weights of the layer, norm, and self-attention layers from a base model, and then copy the weights of the FFN layers found in each expert. This means that besides the FFNs, all the other parameters are shared. This explains why Mixtral 8 7b with 8 experts doesn't have 8 asterisk 7 equals sign 56b parameters, but about 45b. This is also why using 2 experts per token gives the inference speed flops of a 12b dense model instead of 14b.